All right, let's get started. Welcome to ECE421. We are going to study machine learning, a basic introduction to machine learning. Okay, and my name is Ben Liang. I'm a professor in the communications group, and I've taught this course for a few years now. This is the 5th time I teach it. Normally, I teach it with Professor Ashish Kisti, but this year he's on sabbatical leave, so I'm taking over both sections. So this is section 1, so today, and then 2 hours tomorrow, right? Okay. Now, machine learning, of course, is one of the hot topics anywhere, right? You cannot turn on your computer without seeing news items about AI, machine learning, and you see a lot of images and news items like this, right? You have the natural language processing, for example, the ChatGPT that I hope some of you have tried already. Who have already tried ChatGPT yourself? Yeah, good. Don't use it to do your homework, right? But use it just for fun. It's a lot of fun, right? You ask questions. You can trick ChatGPT, you know, right? That because we have some knowledge, right? We're ECE students, so you can. I hope you have tried to trick ChatGPT to give you some nonsensical answers, some weird answers. Yeah, you know, ChatGPT is not supposed to give you truthful answers. It's just supposed to fool you as much as it can. Try to pretend to be like a human being as much as it can. Right? But anyway, you know, to get to this stage where there's a computer there that can really fool you, it's quite an accomplishment. Yeah, it has not been able to. We have not been able to achieve that for many years until very recently. And of course, the medical image processing and so on in self-driving cars, a lot of applications in machine learning. Right? But machine learning is not the idea of artificial intelligence and machine learning. They are not new. As soon as we develop electronic computers, maybe in the 1950s, people have already started to think about, well, look, if we can put vacuum tubes or transistors together and do computation, can we put them together to simulate a human brain, right? So that really was the starting point of thinking about artificial intelligence. The only problem is, why AI was not much use for a long time until recently. Why do you think it is the case? Yeah, we don't have enough computational capability to support the computation needed. Yeah. In fact, up to about 2012, you cannot read this here, it's very blurred, but this is 2012. This is the ImageNet, image recognition competition, okay? And this shows you the error rate, So how much, so this one was 25%, that means that the computer will make error 25% of the time, roughly speaking, okay? And up to 2012, the probability is still pretty high, yeah? But around 2012, something happened. Professor Jeff Hinton from U of T, with his team, developed a new technique using convolutional neural networks to recognize images. And immediately, they beat everybody. There's a drastic drop in terms of the error rate of image recognition. In fact, over the years, we have developed better and better and larger neural networks to recognize images. And in 2015, eventually they pushed down the error rate to 3.57%. Why is 3.57% significant? Well, if you look at the one next to it, this is 5.1. Okay? This one is the human being's error rate on the same image data set. Okay? Even human beings with our big brain, very well-trained brain since we were a baby, look at those images, we may errors 5% of the time. Yeah, but they were able to push the machine to make error below 4%. Okay, better than human beings. Another thing that the machine can do better than human beings nowadays, playing these board games, right? The Go game is supposed to be one of the, if not the most complicated board games developed by human beings, mainly because there are so many different moves that you can make. Yeah, it's a highly complex game. And in 2016, AlphaGo, the machine, finally beat the world champion, a Korean player, by actually quite a wide margin. I think they played 5 games, and then the machine won 4 of them. So quite a dramatic advancement in artificial intelligence in just the last 10 years, yeah, roughly. Okay? So there's no wonder that anywhere you look at the newspapers, you see, oh, there's a lot of money putting into AI, yeah? A lot of new companies, a lot of dollars. Just, you don't have to know the details about these things. Yeah, it's just show you how fast the field is growing, right? By the way, anyone can tell me what's the difference between AI and machine learning? Yes?
AI refers to a wider category, so any algorithm that can be considered intelligent, so like path planning,
yeah.
Chess algorithms that are maybe classical. It doesn't require a neural network.
Yeah.
The machine learning requires a neural network.
Well, machine learning doesn't have to require neural network. Okay, there's but indeed, artificial intelligence is a much broader concept. In fact, it's so broad that it's not very well defined. Yeah, we can't even define intelligence yet, really, right? What is intelligence? Yeah, so now we're talking about artificially creating intelligence. Yeah, so it's a very wide topic, and that pretty much includes everything that we can do. But machine learning, more specifically, has to do with training computers, training machines, using data. Okay, data that we accumulate over time. Yeah, over historical data that we have. So, but this course, we're going to focus, of course, on this narrower scope. Because it's just a single course, right? So we'll focus on this narrower scope of machine learning. And if you look at machine learning this as a topic, you flip through the newspapers or click through the screen, you see a lot of terms, a lot of words. We're not going to, of course, be able to cover everything. Yeah, we'll focus on some basic terminologies. For example, is learning feasible? Yeah, how much can a machine learn? How much can we teach a machine? Yeah? How much data can provide information to a machine? So machine learning, you can define it in several slightly different ways, but we just use the one that from our textbook just to develop these machines, yeah, to train machines using data. Basically, that's what it is. Okay, and there are, broadly speaking, 3 different types of machine learning: supervised, unsupervised, and reinforcement learning. Okay, so in supervised learning, basically we give data that contain labels to the computer. Okay, so we tell the computer, well, this is image of a dog, this image is of a cat. Yeah, those are labels. The dog and cat are the labels. And then we label the images and give it to the computer, and then train the computer to recognize, using this training data, to recognize new images that the machine has not seen before. Okay, so another very popular example, one of the first image recognition jobs is hand-digit recognition. Yeah, the MNIST data set. MNIST, M stands for modify, and NIST is the National Institute of Science and Technology. But anyway, it is a data set that they have. They take these digits from people's handwriting on the envelopes, the zip codes in the United States, kind of like our postal code in Canada. Yeah. So of course, different people will write the same number in slightly different ways. Yeah. But they all have a similar shape, of course. Yeah. you give these images to the computer, but with labels. So these are 9s, those are 8s, yeah? So that you use all kinds of different algorithms, develop different kinds of algorithms to allow the computer to learn from this data, this labeled data, so that the next time you write some number, the computer, of course, that number that you write will not be one of these guys, right? It's a new number, new image that the computer has not seen before. But a well-trained machine should be able to recognize that new image. Yeah? And in fact, nowadays we can do this up to 99, nearly 100% accuracy. Yeah, if you have sophisticated enough algorithm to train the machine. Okay, it turns out to be now a very easy job now. But you're going to experiment with this in this course, yeah, in your programming assignments. In unsupervised learning, basically, you don't give label to the machine, yeah? You do not assign labels to those, say, images or data points, okay? These are so-called unlabeled data samples. You just give them to the machine. What can you hope to do in that case? Well, you ask the machine to recognize the pattern of those data points that you give them, yeah? For example, in the case of face generator, you just give the machine many faces, many images of faces, human faces. And once the machine learns the pattern, or more mathematically speaking, the distribution, the probability distribution of those pixels, it knows, okay, this is the probability distribution for human beings' face. Yeah? And now you ask the machine, okay, generate a new face for me. Okay? The machine can do it. Yeah? That's unsupervised learning. Okay? And I'm sure you have seen this in the news a lot. Actually, fake news a lot, right? People are able to nowadays generate fake images. Yeah? And this, in fact, very human-like faces, they're all generated by computer. Yeah? Nobody in the world looks like that, in fact. Yeah? Well, nobody in the world looks exactly like that. Okay? Reinforcement learning is kind of a way of unsupervised learning. Again, you don't give any label data to the computer. But it's a unique kind of unsupervised learning in the sense that you give guidance to the machine on their actions. If the machine does something good, you give it a reward. If it does something bad, you give it a penalty. Okay? You give some signals, guidance. And the hope is that by guiding the machine, it can explore the environment efficiently, and it will learn about its environment, and then always develop an optimal strategy, whatever you want to achieve. For example, self-driving cars. Yeah? You have to explore, of course, the street, the traffic, and then make the right decision. Make a right turn, left turn, brake. Yeah? And a lot of that is done by reinforcement learning, and a lot of the gaming is also done by reinforcement learning. Yeah? Right. But in this course, we wouldn't have enough time to talk about reinforcement learning. Okay? Reinforcement learning itself is a big topic. It takes a whole course if you want to learn about it properly. Also, to learn about it, we need to know Markov chains. Most of us do not have that Markov chain yet in your probability, right? I think most of the first course in probability will stop before Markov chains. So it'll be difficult to teach reinforcement learning properly without Markov chains. So we won't be able to cover reinforcement learning, but we'll cover supervised learning and unsupervised learning. Okay? And we have linear models, neural networks, and support vector machines for the supervised part. Unsupervised, we have clustering, density estimation, and EM algorithms. Yeah? And how is that related to phase generation? You become clear. Yeah? That's more about the density estimation. Yeah? Detecting patterns in the data. Okay? These are the so-called learning methods. Okay? We will also talk about learning theory. Yeah? Basically, that is about how much you can learn. Yeah? How much a machine can learn, not you can, how much a machine can learn. Okay? There we have this called pack learning, VC dimension. I'm going to go to a bit more detail a bit later. Yeah? And the bias variance trade-off. It's all about talking about how well a machine can learn. How do you quantify that? How do you mathematically analyze how much a machine can learn? Okay. And then we also have some learning techniques that we discuss. That turns out to be very useful beyond the theory, yeah, including regularization and validation. in practice, when you have to make your algorithm work well, these techniques turns out to be very important. Yeah, we'll cover that. But mainly, the course will be, we have a main focus on the fundamentals of machine learning, okay? The fundamentals that have a long-lasting value that will hopefully stay with you throughout your career, rather than the current hot topics. For example, GPT, okay? 5 years later, maybe there's something else now, okay? So we're not going to talk about those just current hot topics only. So the hope is that by understanding fundamentals, you will really properly understand those hot topics as well, yeah? But you have to spend some more time on your own out there to read about it in the news and so on. Yes?
How are the contents in this course like similar to and different from like APS 360?
Yeah, I don't have a lot of knowledge about that course, but what I have heard is that that one is at a very applied level. Really, it has a bigger focus on deep learning. So I would think it's more of a hot topic than the mathematical fundamentals. Yeah. Okay, so let's look a little bit more as an overview of what you will see throughout the course, okay? So we start from the learning methods, yeah? So in supervised learning, we have what's called a linear classification, yeah? So supervised learning, right? So the machine will be given labeled data, yeah? Labeled data, so you have the data points, X, and then the Y is the label, okay? In this case, it's a plus and minus 1, okay, these labels. So this is called binary classification, yeah? Just either this or that, okay? The simple example here. So in that case, you can actually draw or envision these data points as points in space, yeah? If the X is a two-dimensional vector, then this will be two-dimensional space. This plus and minuses, they are the labels for those points, yeah? These are the X's and then these are the labels, the Y's, okay? So the classification basically means that, well, I want to be able to say, well, this side of the space, they are pluses, the other side, they are minuses, okay? So that's binary classification. So therefore, to decide this side on that side, I need to draw a line, right? This is the boundary between pluses and minuses. So after I draw this line, later, when the machine is given a new point, say the new point is right here, yeah? The new point the machine has not seen before, but then it knows that it's on this side of the line, so it knows that it should be a minus, yeah? Whereas on that side, whatever point should be a plus, okay? And that's classification. So this is a very rudimentary, very simple form of classification. And so linear classification because we're drawing a linear line, okay, instead of a nonlinear function for the boundary, okay? So in the linear form, something looks like this, yeah? It's a weighted sum of the x's and so on. Again, no need to know about the details right now. We're going to go to these details right away, okay? Tomorrow, we'll go to this detail, okay? No need to know for now. Just here, I just want to give you an overview of what we're going to look at throughout this course, right? So we're going to have some algorithms to do this, yeah? And we're going to go through those algorithms. And then there's also linear regression. Regression is different from classification in the way that in classification, we have classes, discrete classes that you have to separate the points into discrete classes. Regression, you don't separate into discrete classes, but rather the label is continuous. For example, the credit score of someone, okay? If X1 is someone, yeah, if X1 is you, and Y1 is the credit score that the bank assigned to you when you apply for a credit card, okay? So given you with your attributes, your age, your career, your employer or not, right? And then they will have to come up with a credit score for you, which is Y, okay? So this is called regression, yeah? And linear regression, of course, is just to basically linear fitting, okay, that you have seen in high school, yeah? And linear fitting, of course, we try to minimize the error of prediction or the error of your fitting, right? So some kind of a square error that you probably have seen before in high school, right? But we're going to talk about a bit more about the algorithms and the theory behind it, yeah? That's linear, but of course, very often things are not linear, right? For example, if those are the points that you need to separate in space, in a two-dimensional space, clearly you cannot hope to draw a linear line to separate the blue dots and the red dots, right? Okay, so you have to draw a nonlinear boundary. How do you do that? So it turns out that there's a way for you to transform this space into this space, so that now in this new space there is a linear line that you can draw to separate the points. Okay, so therefore you can use linear classification methods even for nonlinear separation of points. Okay, so that's called nonlinear transform. We'll look at that. Now, I'll say here for regression for line fitting. Okay, in this example, we have the green line, which is the true function that you want to estimate. Okay, you want to estimate this green line, true function. Okay, but you're not given the green line, of course. You're given the blue dots, which are generated from the green line with some noise. Okay, in reality, that's all that you have, right? In reality, you have some observation, but they're noisy observations. Yeah, so the blue dots are what you observe. They are noisy versions of the green line. Okay, and now given these blue dots, you need to develop a computer algorithm to estimate the green line. How do you do it? Okay, so this is a classical regression problem. Yeah, so in the left-hand side figure, you try to use a linear line to approximate that function, the green function. Okay, the red line is the linear line, right? So you do a best linear fit to your blue dots. Yeah, you see, okay, it's reasonably good, but not the best, right? Okay, that's because why you try to use a linear line to fit this curvy shape. Yeah, clearly you're not going to do the best job. Okay, so now it's okay. Of course, now what if I can use a third-order polynomial to do it? So that's in the middle. Yeah, you want to find the best third-order polynomial to fit those blue dots that you have. And that's the one you get. The red line is what you get. Okay, you see it's a much better fit to the true function, the green one, right? Yeah. Now you say, okay, wow, that sounds like, yeah, I need to have more degrees of freedom to fit my data points, right? So what if I go to higher degrees of freedom? What if I use a ninth order polynomial rather than a third degree polynomial? Yeah, ninth order polynomial there. But then you look, if you find the best fit, ninth order polynomial best fit to those blue dots, that's what you're going to get. Actually, not that good fit, right? Why is that? Anyone can tell me why doesn't a ninth order polynomial work better than a third order polynomial? Okay, yeah, it tries to go through all of that. Yeah, that's another way to put this is that it tries to fit to all of the dots, fit to the noise of the data that you have. Yeah, so that's why this is called overfitting. Yeah, you're fitting to the noise instead of the true line, which is the green line. Okay, whereas on the left-hand side, this is called underfitting. You don't have enough degrees of freedom to fit to the data that you have. But that side is also not good. That's overfitting. What you want is in the middle. Okay, just perfect fitting. But how do you do it? How do you achieve that? We're going to talk about how to do it. Okay, and there's some theory behind that, and there's some techniques behind that as well. Okay. And one of the famous techniques to prevent overfitting is called support vector machine. Okay, so basically, instead of just fitting a line, you want to leave a gap. You know, leave some fuzzy space around this line. Okay, so that you will prevent the cases of crossover. You know, the pluses go to the minus go to the plus easily because now you have a bigger boundary between them. Okay, that's the rough idea, but we're going to go to that. Support vector machine turns out to be the best method we have up to 2010. Okay, before the neural network came into the picture. Yeah, this one is a good thing about this one is that it has a good mathematical justification. Okay, we know exactly what goes on. We can analyze this. We can really use rigorous mathematics to talk about how it works, when it does not work, and so on. Yeah. Whereas neural networks, they are a bit iffy. Yeah. Well, we don't really understand how it works really. Yeah. A lot of neural network they work by brute force. Yeah, you try many things and you use a big neural network, and you use some intuition to have a nice design. But then it's not. You cannot be mathematically proven. You know, it's just intuitively, that should be work. That should be good. You know, that should work, and so on. Yeah, that's neural network. But I'll skip this one because there's also a nonlinear form of SVM. Okay. But neural network, of course, is an important method. It is the most important method nowadays since 2010, around that time, because this one has been demonstrated to work very well, especially in image recognition. Yeah. So what it is, we're going to learn about what is neural network and how to train them, and what are the techniques that we can apply, some of those intuitive techniques that we can apply to make them work more efficiently. Okay? And we see the neural network, basically you have neurons, yeah, connected together. Yeah? We have to design the weights, basically the weights connecting neurons. Yeah, kind of like a human brain, right? So that's why it's called neural network. Yeah. And even though we don't have a lot of mathematical theory behind neural networks, we have one important one called the universal approximation theorem. Okay, that says that if you have a large enough neural network, even if it has just a single layer, okay. Nowadays we also call deep neural network, many layers, right? But even if your neural network has just a single layer, if enough neurons in it, you can use it to approximate any function, or at least any practical function that you want to approximate. Okay, so that's why it's called universal approximation theorem. Okay, so that's why neural networks are very powerful if you know how to train them well. Yeah, you can use it for anything really. Okay. Here is reasonable in the sense that there are some mathematical functions that only pretty much mathematicians are interested in. We cannot use neural networks to model those, but then in practice, mostly we are not interested in those kind of weird functions anyways. Yeah. So in training of neural networks, basically we have to establish some kind of error function, or loss function, and so that we minimize the loss, and so therefore it becomes a optimization problem. Okay, we have to minimize the function over some variables. The variables will be the weights of the of the neural network. Okay, we find the optimal weights of the neural network to minimize some error term that we can design later. Okay, and therefore we have a minimization problem. We have to talk about optimization techniques. So optimization is an important topic for this course. Yeah. So the training of the neural network pretty much is just to minimize the errors. Okay, and there's a lot of interesting techniques to do that. But we mostly will focus on gradient descent, yeah, stochastic gradient descent, and so on. There's also an algorithm called the backpropagation, which is the algorithm that made modern neural network training possible. Okay, and that was also an algorithm that's popularized by our own Professor Jeff Hinton. Yeah, the backpropagation algorithm. Since that time, since they discovered that the backpropagation algorithm can be applied to train neural networks, it is much more efficient than the previous method to train neural networks, and that's why we are able to nowadays to train these huge neural networks. Okay, so that one is a very important algorithm to study. Yeah, we're going to talk about that in great detail towards the after the reading week, I think. Yeah. Anyway, we're going to talk about a special form of neural network, convolutional neural network. Convolution, of course, in the sense of convolution that you have learned in your signal systems course. Yeah, and if you remember in signal systems, convolution to help you there's a design filters, right? You can have high pass filters, low pass filters by using convolution. Do you remember? Does it ring a bell at all? Yeah. What does high pass filter do? Can anyone tell me high pass filters? What does it do? Yeah. Okay. Yeah. High pass filter. You let the high frequency parts pass through. You filter out the low frequency parts, and low pass filtering is always opposite. But what can you achieve by using high pass filtering? Yeah, okay. No, okay. In a way, yeah. Low-pass filtering help you get rid of the noise. Okay, that's good. That's good. That's low-pass filtering. Okay, low-pass filtering get rid of the noise because noise has high frequency. Okay, but the edges of a face, the outline of an animal, the edges, that turns out to be high frequency parts. You want to get those out, then you use a high-pass filter. Okay, so that's why I want to use convolution, because now you can train the neural network to automatically decide, okay, here I want to use a high-pass filter, there I want to use a low-pass filter. Okay, and high-pass filter help you pick out the outline of a face. Okay, and later the layers can use, okay, that face is a human face, that outline is a dog. Okay, so convolutional neural network turns out to be very, very important for image recognition. Yeah, we're going to just quickly go through it. I'm not sure we have a lot of time though. Yeah, that's supervised learning. In unsupervised learning, yeah, we're going to learn about how to separate data points without labels, right? So we are giving a bunch of data points, and we're going to say, okay, these points seem to be similar. Yeah, they kind of bunch together, right? But how can you teach a computer to know those points are bunched together, right? Our eyes will look at it, yeah, sure. Okay. But we have a big brain behind our eyes, right? How do we allow the computer to do the same? Okay, so that's clustering. Yeah. So we're going to talk about one method called k-means clustering. Yeah, so that you teach the computer, okay, these bunch are together, those bunch are together, and so on. Okay, and there's an algorithm to do that called Lloyd's algorithm that we'll talk about. Yeah. More than discrete separation of the data points, given the data points, you can also use the data points to estimate the density, basically the distribution of the environment, right? So that goes to what I talked about before, right? The human face generation, yeah? You have to recognize the pattern, yeah? One way to define the pattern would be the probability density function, yeah? How do you estimate that given the data points? Principal component analysis is a topic that we may or may not have time to cover this semester. I have to see. So it has to do with reducing the complexity of the data that you're given into a form that's easier for the computer to digest. Okay? For example, if you're given this kind of data points, at first glance, you may say, okay, yeah, these are two-dimensional data points, right? But then if you think about it, well, I can rotate the space to this form, yeah, then turns out that those data points can be very well approximated as one-dimensional data points. Okay? So these data will be much easier for the computer to recognize or to do whatever processing it needs. Okay? So that's what PCA does to help you reduce the complexity of data points. In terms of learning theory, we're going to study the difference between the training error and the testing error. Yeah? Training error is the error that you gain with the training data points. Test error is the one that you really are interested in when you go to the outside world and test the computer, yeah, what error it makes. These two obviously will not be exactly the same, right? But you want them to be close enough, yeah, so that when you reduce the training error, the test error also is small, yeah? So that has a lot to do with learning theory. In particular, we're going to study the idea of probably approximately correct learning, okay? Sounds like a lot, right? What is probably approximately correct, okay? It has a very rigorous mathematical definition for that, and we're going to develop some mathematical formulation for the theory of this pack learning, yeah? A related topic is the VC dimension that has to do with how complex your learning model is, yeah, or how complex your neural network is, yeah? In general, of course, it's a bigger neural network is more complex, right? But how do you mathematically quantify that? Yeah, and just now we talked about the example of using a linear line, third-order polynomial or ninth-order polynomial to fit your data, right? So which one is the perfect one to use? Well, you have to have some way to quantify that, how complex that model, that polynomial is, okay? And VC dimension is one way to talk about that. Learning techniques, validation, it has to do with just checking how good your learning is while you're training the machine, okay? Earlier I said there's a training error, there's a testing error, right? So you want to, while you're training, it would be nice to know whether this algorithm will work well, or this machine that I train will work well when I bring it to the real world or not. But before I bring it to the real world, how will I know whether it will work? Okay, so that's validation. Okay, we're going to talk about how that works. Regularization is another one of those techniques that can help you stabilize your computation, make your trained model more robust to noise and so on. Yeah, and these techniques, a lot of them, you will have a lot of practice on your own through the programming assignments in this course. Yeah. Okay, so any questions before we go to logistics? Yes. I don't use PowerPoints. I will just write on the screen, so I cannot post what I, yeah. Yeah, right, only for this one I use PowerPoint. Yeah. But I would, yeah, I know people might want to have it ahead of time, right? But pretty much like writing the board. In the past, I always write on the boards. But I know these days people seem to prefer the screen more than the board. At least more people nowadays. So I try to write. Another good thing about writing on the screen is that I can just post whatever I wrote after the class. Yeah. And that's what people have been asking me to do for many years. So, yes. I will post the slides, yes. I will post the slides. Okay, so some basic logistics. The textbook is this one. You should get the copy of this book, okay? It's a very nice, really written textbook. We like it here in ECE because it's more mathematical than the other alternatives, okay? It actually talks about the learning theory very well, yeah? And so that's what I said, we want to focus on the fundamentals, yeah? And the book has a website. Over there, you also find new chapters. This book itself is very thin, okay? But it has many chapters that are not printed, but rather the authors added later after the book went on print, yeah? Those chapters, actually, they are very important. For example, all of the neural networks, they are in the electronic chapters. So make sure you get those chapters as well, okay? You need to get a password to access those chapters, and that password is given when you buy a book. Also, yeah, on the website you can find some video lectures by Professor Abu Mustafa from Caltech. He's very good, yeah. It's very different from our course, okay, because the focus is different. He just covers from the book in chronological order. We cover things quite different, but very nice supplemental material there from this website, okay. Just a word on prerequisites. Probability is definitely prerequisite, okay? If you don't know probability, you should not be taking this course, because as you have seen just now, right, a lot of this learning has to do with noise, has to do with probability, you know, whether how likely this will work or not, right? We talk about expectations, we talk about variances, yeah? So you need to have those foundations of probability very well, yeah? Linear algebra, if you know linear algebra, will be very helpful, but I believe that most of you have taken a course on linear algebra, right? Yeah? We're going to do a lot of vectors and matrices, yeah? So you need to have some foundation. But if you don't feel very comfortable with linear algebra, since it is not officially a required prerequisite, if you don't have that yet, you can catch up, okay? In the textbook, at the end, there's an appendix on the basics of linear algebra, but online you can find plenty of tutorials and online free courses on linear algebra that you can go through. I think I can post some material on linear algebra as well on Quarkus, okay? Programming, you need to know Python. I hope you all know Python by now, right? It is really the programming language of the day, right? We use PyTorch, which is a package that has many machine learning libraries built in already, so you can just call those libraries, very convenient, yeah? That's the prerequisites. Now let's take a quick look at the syllabus. You have that. I'm going to set up I have the email here, but there are 200 students across 2 sections, okay? Emailing is probably not the best way to get in touch with me, yeah? So unless it's some kind of more of a administrative issues. But for most of the course technical issues that you want to discuss about the lectures, post your questions on Piazza, okay? And also the reason is that for those technical questions, if you ask them, most likely there are 10, 20, 50 other students having the same question, right? I'd rather just answer them in one shot and then replying everybody's email, yeah? So emails only for administrative issues. What else? Textbooks, yeah. There are two recommended textbooks as well. One is on deep learning, especially when we go to neural networks. You might want to grab that book. It's free online anyways, yeah? There are some chapters there that we will assign as reading for this course, yeah? That deep learning book. And then we have the last one, the third one is a older, more classical book on machine learning before 2010, yeah? But that one is focused more on image processing and video processing. If you're interested, that one is a good book to read. It's one of those classical books on machine learning, okay? Now, homework, I will assign weekly homework, and then you need to finish your homework before you go to the tutorials, okay? And every week you have to submit your homework on Quarkers, yeah? But because this is before the tutorials, I just want to make sure that you all try these homework problems before you go to tutorial, okay? And so they will grade it only by your effort, okay? Not by correctness, yeah? Just to try to do them, and then you go to tutorial, because otherwise I don't think tutorials will help if you have not looked at those problems yet. You just sit there and just listen to the TA give you the solutions. That doesn't help you. This is a very mathematical course, okay? So doing your own work, paper and pencil work is important, okay? Yeah. But we also have programming assignments, of course. After all, this is a interdisciplinary course. Yeah, we both have mathematical theory and practical aspects of learning, right? So you will have 4 different programming assignments. They are pretty short, pretty simple, yeah? Especially when you get to the stage where you can, when you get to use the libraries in PyTorch, yeah? The beginning ones, you have to write your own code, your own learning algorithms, but later you can just call libraries from PyTorch. So that's 20% of your work. You can form a team of 2, or you can just do it by yourself, okay? Up to you, yes?
So only the programming assignments is, like, can have groups. The homeworks are individual.
Yeah, homework is individual. Yeah, definitely. You have to. It's a paper and pencil kind of work, right? Yes.
Will there be 10 homeworks in total?
Depending on how many tutorials, I think there are 12 homeworks then. Yeah. Yes. Say again? No, you don't have to. You don't have to. This is only tutorials only for the homework problems. Yeah. Yes, I think so. Yeah, mostly from textbook. Almost all of them. Yeah. Okay. Midterm exam. Now, currently, I set the day, which is a Tuesday on May the 5th, evening 6 to 8. But someone already told me that there's another exam on that day, on that evening, the networking. How many of you have a conflict on that day, Tuesday evening? Okay, how about Monday evening? How many of you have the Monday? Yeah, kind of have. Yeah, I know. Yeah. So I know when you have 200 students, we always have this issue. Yeah. So I'm going to set up a survey on Quarkers, and the majority wins basically. Yeah, maybe these 2 days, and then I have to make special arrangements for the other group. Okay. Yeah, there's a course schedule there on the syllabus as well. The syllabus is on Quarkers, of course. So roughly we'll follow this schedule, okay? We might change depending on our progress, but likely not. And I'll try to keep the 2 sections, O1 and O2 lecture sections, at the same pace as much as I can. So in case you want to jump between sections, feel free to do so. It doesn't matter. This is just me, yeah? Okay, any further questions? Yes?
Sorry, you said that if we want to do like one of the lectures from one section and the other from the other, is that all right?
Most likely should be okay. Yeah, I'll cover roughly the same thing. Yeah, there's always a small risk that you might miss something, but Okay, then I'll see you tomorrow. Yes.
I think I'm in one of those unique scenarios where I have a conflict on both the Tuesday and the Monday.
Okay.
What would we do to work out that?